Hi everyone, thank you so much for joining us for a very special guest speaker session today. We have with us Antonio Orvieto. I hope I pronounced it correctly. Antonio is a principal investigator at Alice Institute Tübingen, an independent group leader for the MPI intelligence systems. Antonio leads the deep model and optimization group and is a lecturer at University of Tübingen. Today he will be presenting one of his research paper in search of the Adam secret sauce. Thank you so much, Antonio, for joining us and taking out time. I'll hand it over to you.
Thank you. First of all, you hear me correctly? It's all good? Yeah.
Yeah, thanks.
Okay. Amazing. So thanks all for the invitation. This is super great, and I'm always up for talking about Adam. Adam has been on my mind for a long time. So I felt like this spring, so in search of maybe my own identity, I did a lot of ablations, and I kind of shared the results in this paper. So yes, I'm gonna talk about it. But first, also, I mean, I'll make an overview a little bit of what's this about, and perhaps also, since some of you might not be super familiar with optimization in general, basically half of the time I'll be talking about what other people did, just to summarize a bit where we stand in terms of our understanding this optimizer and why it's important, and also what are some of the open questions and motivations that we see in the literature. Is a very exciting topic, understanding optimizers, and try to come up with explanations and try to maybe, I mean, it's a leitmotif of all deep learning, like explanation is lacking. We also have it on the optimization side of deep learning. And sometimes people kind of like, I was asked many times, like, why is that we don't understand things? It seems like many people are doing math of optimization, seems paper every day. Why is that we have this optimizer since 10 years and we don't really understand what's going on? So maybe I'll try to give you a walkthrough of why we don't know, or what we know and what's lacking, and partial answers. So I'm gonna start by motivating by introducing what Adam is and motivating what we don't understand, and like perhaps why it's important. Part one is gonna be a large scale ablation on language models, giving evidence of some hyperparameters being equal, yielding to good results. And second part, it will be about the secret sauce. So it will be like, what does this information that we get empirically give us through a theoretical analysis about Adam and about what is needed actually to optimize these very large models. So this slide is old. I've been presenting this slide over and over. I have this young Pope quote saying, who's the most important author? I would say optimizer of the last 20 years. And then there's this beautiful quote like, careful now, not the best. Virtuosity is for the arrogant. And I think that's exactly what's happening. I mean, we know that there are a lot of optimizers with amazing theoretical properties, but perhaps it's not what matters. What's the optimizer that has had the most impact the last 20 years was Adam. And we also have a best test of time award this year in iClear, exactly for Adam. One of the most cited papers in deep learning proposing this new optimizer that you can call with PyTorch with this one line above. You probably all know what Adam is. But for those of you that are not very familiar with the form or just don't care, and some things, like if you do applications, you might have never seen what is actually happening under the hood. Let's take the weight WI of a neural network, and we want to update it. So for that, we use gradients. Here are gradients, so like a gradient with respect to the ith neuron of the loss. This is what is written here in the second line. We also square it. We take moving averages, like this beta1 plus 1 minus beta1. We have these parameters m and v, and this is the update formula. It looks a little bit strange. One can make sense of it. Looking at for a long time, as I've been having, like, you think at some days you think you understand what's going on, some days you're like, could have been different. In some way, like, there are some relations to our algorithms. Some people in deep learning say that it's like kind of scale invariant, or like you don't need to tune the learning rate if you use Adam, and that's the beauty of it. Not true. You still have to tune the learning rate, but in some way, this is very, very, very much used everywhere, really. So these parameters that are the betas, the learning rate, and You can set them in the Adam optimizer. Those are usually set beta 1 equals 0.9, 0.999 for beta 2. Epsilon is a small regularization factor. Some people claim a lot of importance to that. Then there is the learning rate and perhaps a scheduler. So this basically is like taking the, if you want to simplify it in your head, like you take the sort of like a smoothed version of your gradients, a smoothed version of your gradient squared, and you divide by one by the other, and you follow that direction element-wise with a certain strength. And that's basically what Adam is. Makes sense? Can make sense. The question is mostly like, why is that the thing, right? I mean, it could make sense. A million other things could make sense. Why is this thing making so much sense? That's perhaps the question that has been going through my mind for a long time. So that's basically like kind of in a nutshell what's happening. If we talk about EMA, so exponential moving average, you can think about it as a smoothing your gradient signals, moving the gradient signal squared element-wise, dividing one with the other. If you decide just to use the square, when you have this RMS prop algorithm, you just have the square root of the square on the denominator and following the gradient with that adaptive step size, which is eta over the square root of v, then that's called RMS prop. That was proposed before Adam, and Adam is basically, in an optimization sense, momentum on top of RMS prop, in some sense. It could have been another way. This is the way that works best. And just to remind what is an exponential moving average, let's take a function, that is the blue function, the signal, and let's do the EMA of this. The EMA of a function is basically an online thing you can compute. And so there's the orange curve is the EMA of with strength 0.5. So basically you're very similar to the original signal and not very smooth. As you increase the beta parameter, so this goes to 0.9, 0.999 and stuff like this, then you become smoother and smoother, but you also become more and more different compared to the original signal. Unfortunately, you cannot have both at the same time. You cannot have something that tracks the signal very well and being so smooth, just because it depends on the velocity of the signal and kind of the frequency component. This is basically a low-pass filter. So you low-pass filter the gradient, you low-pass filter the gradient squared. The division of the two could make sense. You follow that. This is kind of an illustration of what these things are doing. Of course, the signal is the gradient, so it's something that you only know as you unroll the iterations. So you do this through a online update. And why is this particularly crucial, this algorithm? I mean, we all know that stochastic gradient descent is also a good algorithm, and it's quite different. It's a more simple algorithm that can be used for many things, but not for language models. So, and also not for all attention-based models. So if you have an attention-based model that can be a language model, but also kind of a vision transformer or a graph neural network, like a graph transformer, then sort of Adam is really, unless, I mean, one thinks about very recent developments like muon, then it's kind of is the state of the art of what you can do. It's the most reliable algorithm. That was also mentioned in the Test of Time award. Adam is very reliable. People trust it very much. It works very well. And if you really have to put your money into that, that's kind of what happens, right? When you train a very large model, yeah, you bet on Adam. Okay. And this, the first thing which is interesting, and the kind of one of the first paper outlining this discrepancy between the performance of Adam and other optimizer is this 2020 paper on layer normalization. So we're not going to discuss layer normalization. This is just an example that shows, in this paper I show, okay, effective warm-up, you need other things to train transformers, but if you don't have Adam, you're not going to train this. And you can see this in the plot. This is blue score. This is, of course, 2020. It's not language model. This is kind of a another thing, right? As a kind of a BERT style transformer, and for translation. And you see that basically the performance of SGD is much lower than the performance of Adam, even if you include all the tricks that are in the book. Yeah. And you can see, okay, so where do you see this? On the A figure is Adam, on the B is SGD. Notice the blue score, how low it is for SGD and how hide is for Adam. Of course, there is the warm-up effect. If you don't have warm-up, also Adam may be not very good. At least for this layer normalization, this is a completely different paper. It's just like, there are these plots here and there early on saying, if you actually use SGD, you don't get anything out of this. Why is that people think that attention is particularly relevant in understanding the gap is because in attention, you have two sorts of parameters. You have parameters inside the softmax and parameters outside the softmax. If you're familiar with the mechanism, you know very well what I'm talking about. You have this pink parameters and you have the yellow parameters. They have a completely different role. Some mix the tokens, some mix the features. And it is also has been stated that if you have this sort of heterogeneous structure in the Hessian or in your network, like you have parameters dedicated to doing something and parameters dedicated to doing something else, then you're sort of asking the network to do different things, or they act at very different scales. And these different curvatures, if you want to be mathematical about it, result in the need for having an adaptive method. That is a method that can adapt to different blocks. And that's why Adam is so good. It might be a bit unclear why is it doing it. If you are curious, read this paper. It's just like people have been noticing this gap, have been reporting this gap a lot. And there is explanations of why. This is the Hessian heterogeneous structure that you can find in some language models or VATs, kind of elucidating a little bit this difference between early models and models that we have today. And this will come, I will also refresh a little bit on the history of Adam. At some point in the past, people did not use Adam because SGD was performing better in some regards, but those networks are the one that you see on the left, which are all the blue networks, which are very homogeneous. Networks of today are heterogeneous, blocks of different nature, and for those you seem to need this Adam optimizer. There is also a lot of other explanations that involve noise, heavy tails, clipping, all sorts of stuff. Just to name a few, there's many excellent papers about the Adam SGD gap and about why Adam performs so well. It's kind of a whole research area. There are people doing PhDs about it. But if you look back, as I said, in 2017, the picture was not as clear. There were not papers about why Adam is so much better than SGD, because as you can read, for example, from this 2017 paper, let's read the abstract, the last line. These results suggest that practitioners should reconsider the use of adaptive methods to train neural networks. I mean, if we were to follow this suggestion, we would never probably have language models at the level of today. But this is a solid piece of research showing that there might be problems of Adam. So Adam is not in general a better algorithm. It just looks like for the methods that for the models that we have today, it works very good. But understanding this is super important. Let's also like go step by step. So 2015 and 18, people were using Adam, but we're also saying, yeah, you should really use SGD if you can. It's a little bit slower, but in the end, it will pay off. Also in 2018, I was doing my PhD, and I remember people clearly being worried about, Adam does not converge. The proof of convergence in the Adam paper was wrong, plain wrong. There was a crucial mistake. And so people were saying, okay, no, now we also know that the proof is wrong, plus it doesn't generalize so well. Maybe it's just a bad algorithm. There was kind of a vibe in 2018. People were doubting that Adam was so good, but now here we are in 2025, just using Adam. And a big part of it was that in 2018, the group of Frank Hutter found that there is a detail that was kind of wrongly implemented in Adam, that is regularization. At the same time, around 2018, transformers were born and transformers were optimized with Adam. And notably in language models, the effect of weight decay and regularization is a little bit funny. So people were just caring about the speed, and Adam was performing very well. But it was also kind of restricted to language. As soon as transformers became also prevalent in vision, people started to pay a lot of attention, and people just started to just optimize the network with Adam. I would say between 2019 and 2025, there was basically nothing else. We have seen good things happen in 2023. There are definitely other algorithms we can use. You can use Lion, Sophia, but really, like, just for a very brief amount of time, people were considering switching. So one of the early explanations was that it's text. text language model is so hard, but you need Adam. That's the reason why nowadays we are sort of believing it's more about the heterogeneous structure of transformers. This is, by the way, the AdamW difference with Adam. So if you know AdamW, that's the difference is that you implement regularization differently. And so basically, like you see that early on, this is a very early plot, like in the literature from the AdamW paper, showing that indeed the early Adam had problems and now it's fixed. So now we can say, okay, there were some initial problems with Adam, now it's fixed. And also in optimizing normal neural networks, non-transformers, it works kind of well. Still, for some tasks, SGD is used. It's not all that only Adam is used. Still, there is a lot of excellent algorithms with the very principled theoretical guarantees that are used for very specialized tasks. You should not just throw Adam at everything. But definitely, if you have a language model like I personally would not consider anything else unless one really sees that muon performs better. We'll get back to muon in a second. So the first motivation of this paper, let's go to the motivation part, is to understand this. Simply because, I mean, we are using this thing so much, and there has been many explanations, but we really lack a little bit of formal, kind of a rate, a convergence rate, or a very quantitative thing that is like, oh, okay, like there is a theorem associated with Adam SGD. So that's the motivation. Many people are drawn to the gap, many theoretical people, because yeah, there should be a theorem about it. There should be something that, some characterization of when we need it, why we need it, and that's kind of lacking. There has been attempts, very good attempts. Perhaps some people consider it solved. But the reality is that it's not very clean also because Adam does indeed have some convergence problems for some hyperparameters, and there has been excellent papers analyzing that, and I'm going to go through that. But just so you know, there is theory about Adam and SGD. Sometimes theory is not as powerful to predict the gap, or kind of is a general theory that doesn't really model this gap between SGD and Adam. There has been excellent work by Fred Kunstner, shout out to him, and many other colleagues that I'm going to cite also later. The second motivation is my favorite, new capabilities. And then I'm going to be a little bit of a drift up to, I mean, half the time I'm talking about optimization, half the time I'm talking about new models. Let's take Mamba. Some of you have seen that. I mean, Mamba is an excellent alternative to attention that is much faster in some context, like, for example, if you have a very long sequence compared to flash attention. So there are new models that are emerging that are beyond attention. And this kind of is a trend in deep learning in the latest years, going beyond attention, going like really squeezing out everything we can from our GPUs. And that implies that there are new models. Okay, good. That's very good. O of L complexity instead of O of L squared. L is the sequence length. Very good. But this is really what we want. We want to go beyond attention, beyond transformers. People have been reporting, though, that these models, though they are very fast and they're very, they're very strong, they lack a little bit of capabilities sometimes. And so this might be due to different reasons. It might be that the models are not having the right inductive bias, or it might be that they're just not good enough. What we found, and this is another paper, I'm just going to go to the point here. The point is that it's not just that. These models, these new models that we really want to optimize because they're very nice and we really want them in our pipeline because they're much cheaper at inference, for example, we cannot optimize very well. So this is the learning rate sensitivity of Mamba, the orange curve, versus attention, the green curve, for a task that is associative recall. It's a basic fundamental task in language where you see that attention works very well for basically all learning rates. But Mamba, and talk about this figure on the bottom right, works for only one learning rate. And if you move a little bit, it doesn't work anymore. What does it tell us? It tells us that the model has no problem expressivity-wise to learn this. It just is very hard to optimize. What does it mean? It means that we should go beyond Adam maybe for this. We should design maybe a better model. That's another way to do this. But in general, it is possible that if we don't understand our optimizers, when we have these sort of problems, if we understand our optimizer better and we understand what are the problems and the scenarios that it can tackle, maybe we'll never have this problem again in the future, where we have this confounder of optimization. So it's important to understand this for the theory of it, for the science of it, but also practically speaking, optimization is a confounder. Optimization for deep learning research should not be a problem. It should be that you throw your optimizer at it and you trust the results. And if your model is not able to do it, it means that your model is not good, not that your optimization failed. We should not have failed optimization cases, but we have it. And we have it for Adam. So it means we should go beyond. And we knew this, by the way. The optimization for RNNs is an excellent research topic that is unsolved. And we still don't know really how to optimize them good. So perhaps it could be muon, right? This new optimizer that has shown remarkable efficiency in language models. The problem is that on some parameters, muon still requires some Adam inspiration. It is promising, but we will see where it goes. I am personally very, very hopeful that the muon Scion, gluon, and all the other excellent Polar Express and all the other excellent papers about this topic. Like I think there is definitely some truth and definitely some way to go forward. But just to showcase that Adam, even although we have new optimizers, is still deeply rooted in there. I like to have a quote from this paper. Of course, we all know, like, now Kimi is trained with muon, but if we read the paper, the original paper of scaling muon, we read AdamW is used in couple with muon to handle non-matrix based parameters, I mean RMS norm, LM head, embedding. And what they do is they propose to match the other parameters RMS norm with the one of Adam. So you see that there is some inspiration. If you know shampoo, that's another optimizer, the most powerful variant right now is called soap. And this soap optimizer actually operates in the Adam eigendirections, like directions. So there is a lot of Adam also in new optimizers, like, which is completely fine. It's like going beyond Adam, but on a different axis. It's not really because we understood Adam that we could do this optimizer. Is more like we're trying to go beyond, even though we really don't understand what's going on. Third motivation, simplified models. And this is the most relevant motivation. To understand something, one of the most amazing ways to do it is to simplify it. Like, so you have your Adam, so that's the first line. You have this M and V, momentum, and second moment, or something like this, with that use different parameters of the moving average beta 1 and beta 2. And by the way, these are always kind of different. In Vision, back in the days, it was 0.999 for beta 2, and nowadays it's 0.9 for beta 1 and 0.95 for beta 2. And if you look at all the code bases, usually those are not tuned. Those are usually just used in this form, and what one usually tunes is the learning rate. So if you go from Adam, as we saw, if you take beta 1 equals 0, then you get RMS prop. You can go even more. You can say, well, let's say beta 2 is equal to 0 and also epsilon equal to 0. Then you get sign gradient descent. You follow the sign of the gradient. You don't care about the magnitude. You just +1 or -1, and you follow that with the step epsilon, eta. If you reintroduce momentum, and you get what is called signum. There's a paper by Jeremy Bernstein in 2018 about this method and studying convergence guarantees. So in some way, like, going from Adam to signum, it kind of looks like a straight path. Signum could be a very good method, or sign on gradient descent, to kind of understand what's going on. So in some way, and that's kind of a key element in the talk, like, sign gradient descent is often used as a good proxy for what happens in Adam. And so in some way, if we understand Adam, like, it could be that it's the reason why is because similar to sign gradient descent, or sign gradient descent brings about some insights. And there's a couple of papers about it, or more than a couple, that relate Adam to clipping and to sign descent. This is, for example, like, there is an excellent paper by Fred Kunstner, like, noise is not the main factor between behind the gap of SGD and Adam in transformers, but sign descent might be. It's basically saying, this kind of recent 2023, saying that, and you can see this from the plots, that actually sign gradient descent and Adam can be very close in performance and much better than gradient descent. But you see from the plots down that it's true, but also some gradient descent can also perform a little bit worse than Adam. So in some way, like, that's the interesting bit. Like, we want to really go beyond Adam. If we reduce Adam to sine gradient descent, can we really understand what's going on? And can we also go beyond that? So I see a couple of forward questions. This is not really a problem with these papers. Like, they are outlining a strong connection between Adam and sine gradient descent, which is, again, this line of thought. This is not a problem. This is actually super interesting. What we ask here is a further question. We ask, how precisely big is the signum Adam gap in standard language modeling? And again, we like signum because it's a method that is simple. We can understand this. We understand this a little bit more, let's say, than Adam. So it's in our mind, it's one line. It's much simpler to understand. So we want to understand, okay, is there a sizable gap between the two methods? And if not, is that all? Like, what is really that is missing if there is a gap? So I got a little bit obsessed. I tend to do this in other things as well, but mostly about Adam. So I spent months tuning optimizer and language models. I think now I trained more than 2,000. The ones that I report in the paper are now 1,800, but there's many more. And really, like, this is the configuration. It says, like, okay, so this is okay, it's a nano GPT. I'm just gonna say it's nano GPT, but there is rope, which is, so it's a modern variant. So it's uses all the recent tricks. This is a basic configuration, but we have different sizes, different data sets, everything. Okay, so there's nano GPT. We use rope, RMS norm, pre-LN, of course, Swiglu. Instead of MLP, we GPT NUX tokenizer, bfloat 16. We use a learning rate scheduler, which is the usual warm-up cosine. We clip the gradients. We report always validation, and we don't have weight tying. We have two model sizes, 160 million parameters and 410 million. We use PTI configuration. So all of this is like done really with no cherry picking. We're just like doing this at a setting that makes sense. And the main reason why is because this is driven by my career. This was a set of ablations just right after, like after a while, a few months, we actually decided to make a paper out of this, me and Robert. But it wasn't really decided to be a paper before this. We didn't do the paper and then did the ablation. It was the opposite because the ablations were very interesting. So we have two sizes again, and we use rope, we use pre-LN, blocks are scaled in nano-GPT way. And if you want to know where's the code I didn't write, our excellent research engineer for the OpenURLM project, that is a project about safe and modern LLMs for Europe, wrote this. So this is available at plain LM, like in the GitHub. So there's the link. And also, by the way, if you're a research engineer or an engineer that really wants to build something that is open source, you can submit our application to us because we are the best. Just kidding. This is this is the setting. This is setup. Again, is a setup that is, I think, aligned with many of the recent practices. And there's also variations that one can do. For example, one will be QK norm. Interesting. We didn't try this. There's other things that one could do as well, Z-loss. There's a million things. One can also try different configure, like sparsity. We are in a very standard setup, very aligned with the configuration that we have with PTI. So what we do is a lot of experiments. Like, so for example, here is how it looks like for RMS prop. So, and why do we do this? Again, the reason is we want to really see what is the gap between methods. And we don't want to be biased. We just want to collect data about, okay, this is the best the optimizer Adam, the optimizer RMS prop, the optimizer Signum do on language modeling. And the crucial thing is, like, how big is this gap between sine gradient descent that is a method that we understand, and Adam, that is a method that we potentially don't understand. By the size of this gap, we will judge, is Adam doing something special? And if so, what's the secret sauce? Okay, so for example, here we have a scheduler that we don't tune. I mean, it's fixed for all the experiments. And we have the learning rate, eta, and we have the beta 2 hyperparameter. And we have this sort of plots. And all the plots are in the paper and all the runs are in the GitHub repository. Like you can download all the traces for all the training losses and all the configuration of the parameters. So here, for example, you see beta 2 on the top. So we try a lot of beta 2s. Until we find the best one for the best learning. So for example, here, when we say performance of RMS prop, we mean the best performance across the tuning of beta 2 and eta, which in that case, this case is around 20, I don't know, 26, something like that. Is this point at beta 2 equals 0.8. Turned out that it's 0.8 for this particular configuration, which is one I'm going to report in the next slide. So if we do this for all methods, and that's a lot of runs, like really a lot, we have gradient descent with clipping, global clipping, sine gradient descent without momentum, sine gradient descent with coordinate clipping, RMS prop, signum, and Adam. We take the best configuration, we run 3 seeds. This is again trained chinchilla optimal, so 3.2 billion tokens. Slim Pajama is the dataset. Sequence length is 2048. We have a batch of 2256. This is kind of usual stuff. We implement this with gradient accumulation. We use only one GPU, which is an A100 with 80 gigabytes of RAM. So our batch size, micro batch size is 32. Our accumulation is 8. So we run 8 times. So kind of a normal setup. It's small scale because it takes like 5 hours and a half for each run. It's still kind of, I would say, much larger scale than most optimization papers. So after this around 600 runs, we have this table, this little table, which comprises the result of 600 runs. That is saying that Adam is indeed the best. We have weight decay, so this is AdamW actually, but let's say it's Adam. Because all the methods have some sort of weight decay, we tune it a little bit. You see that the gap between Signum and Adam is around 1.5 perplexity. Perplexity is exponential of the loss. And if we see the performance of gradient descent, that's 53. So sine gradient descent with momentum is super close to Adam compared to gradient descent. However, is this 1.5 something we should worry about? This is the crucial question, because it's 96% of the gap is closed by Signum. But is 96% enough? Remember that we want to go beyond Adam, not beyond sine gradient descent with momentum. So we want to really operate in a regime where we understand even how to get the one perplexity more. But come on, it's one perplexity. How bad can it be? Actually, it's pretty bad. It means it's 25% slower. So how do you assess this scientifically? And this is also very important. When you compare training at different token sizes, token budgets, you should never compare curves one by one and compare where do curves intersect and stuff like that. The best way to do this is try to train for a smaller amount of tokens. Train it for shorter. So here is AdamW 3.5 billion. This is the number of tokens here in the x-axis. And you see that if you were to train Adam for 2.4 billion tokens, you would have reached the same performance of Signum, but on 3.2 billion tokens. That means 25% slower. So you could have saved 25% of your GPU time if you were to just use Adam. So on the other sense, like you are losing definitely something when you use sine gradient descent with momentum. And so this kind of motivates the fact that, yeah, there is kind of something more. And this might not be, and I'm not saying that this is fundamental for all sorts of isolation. I'm saying very practically speaking, 25% is a lot. And if we really want to go beyond Adam to improve what we have, we should try to understand what's this little gap. And again, papers talk about the similarity between Adam and Signum, but no paper really tries to get a deep dive into this little secret sauce. But again, now we're back to square zero. What do we do? Fortunately, we notice something else. So this is an ablation that actually shows first row signum. Okay, so you have signum plus weight decay, you have the momentum parameter beta, and you have the learning rate. Okay, we have also ablated clipping, if true, if false, because again, I'm obsessed. And then you see what is the lowest point in the curve. Okay, so that's the reported performance. We draw this as a green line in Adam. And let's look at the Adam curves now. On the top, each of the plot, each of the panels is for a different beta 1 parameter, numerator, the one controlling M. Each color, beta 2. So, and for each one of them, we have a learning rate. So again, it's a three-dimensional tuning. What I'm showing you is three-dimensional tuning. This is more complicated. What we noticed is that beta 1 equal beta 2 was performing very, very well. Always the best. Sometimes a little bit different, but as you can see, like we're not very far away, especially if you consider the green wall that is signum, you see that most of the Adam runs are better than signum. So we thought, okay, but actually beta 1 equal beta 2 is kind of giving us a lot of the performance of Adam. Maybe there's a 1% missing sometimes, but it's definitely better than 25%. And actually, most of the time was kind of the best. Also, let's scale it up. Okay, we saw it for one setting. That was, again, chinchilla optimal, 160 million parameters. That means 3.2 billion tokens and a batch size of 256. Let's try to scale up the model and be, again, chinchilla optimal. This is trained on 8 GPUs for around 5 hours. And these are a bit less runs, but you see that the tuning is the correct one. Like we are in between beta 1, the optimal beta is in the middle. Beta 2 is never at the edge. You should always check for these things when doing proper tuning. You can see that beta 1 equal beta 2 is really like reasonably the best. And also you see another thing, which I kind of a shout out to some of the new people. Be careful when doing your experiments because, for example, here, beta 1 equals 0.9 and beta 2 equals 0.95. That's the red point here. That's not the best Adam performance. The best Adam performance we got from beta 1 95 and beta 2 equal 95. This is a very sizable gap. 0.6 perplexity at this scale is a lot, like really, really a lot. And so like always when comparing optimizers, one should be careful. Of course, one cannot do everything. But this is what's the point here is that beta 1 equal beta 2 was kind of good. But okay, this more model size. Let's do even more. Let's do different batch sizes. Smaller batch size. Curves are a bit more noisy. But we see that we are pretty good. Like we can get more reasonably good performance. Like again, like there are some noise. It might be that sometimes a beta 2, which is slightly higher or slightly lower, gives a good performance. But you know, we're kind of satisfied. That's the point. And also if you have to tune one parameter, if you don't know how to tune them, you can tune beta 1 equal beta 2. I mean, it's a kind of eliminating one axis. So again, tuning 3 of a parameter is always better than tuning 2. Always. Like, always. But again, if you had to tune 2, you could pick a beta 1 equal beta 2. This is 256, but on less tokens, because we do a lot of runs here. So like we need to consume a little bit less. So we have 2.5 billion tokens instead of 3.2. But that also counts as like, less tokens. It's another setting. Here we see it's perfect, like every single time, beta 1 equal beta 2, 256. If we are 512, we might lose a little bit sometimes, but it seems like very noisy to use this beta 2. Okay. What about more data? I mean, for practical purposes, we use less data than chinchilla optimal. Reviewers asked, I was personally very glad to do the experiment. Because it's super interesting and the results were super good. So if you actually train for double the tokens, you see beta 1 equal beta 2 as the choice here that highlighted. You see that if you were to tune only beta 1 equal beta 2, like that means you choose beta and you set beta 1 equal beta and beta 2 equal beta, if you were to tune this, instead of tuning all of this table, and again, here, I'm not showing this because this is a screenshot from Open Review, but we're doing all the learning rates as usual. If you were to only tune one parameter instead of two, you would have gotten 19.73, and the best thing you can get tuning two parameters is 19.72. So maybe, yes, a little bit. But again, there's noise. And again, like you're having a lot more compute. Like here, this is basically 6 times more compute for 0.01. I mean, so pros and cons, right? So it works very well, even if with the double number of tokens. And here's the secret sauce. Okay, so ask the question, what is really happening under the hood if beta 1 is equal to beta 2? Let's drop epsilon. Some people will be cringing right now. Oh my, you cannot drop the epsilon. Let's drop the epsilon. We have ablation also in the paper showing that the epsilon parameter was not very important. We can set it to 10 to the minus 15. Doesn't matter. The performance is still very, very good. We have a table about this in the appendix. So we feel comfortable about taking away the epsilon for now, just for get a little bit of insight. And here's the thing. The direction that we're following is the EMA of the gradient divided by square root of the EMA with the same parameter beta, is the point, of the gradient squared. And then we have a proposition. If beta 1 is equal to beta 2, then Adam can be rewritten in this sense. That is the momentum, m, over the squared of the momentum, plus this beta times EMA with parameter beta of the difference between your gradient and the momentum. So if we set this as an estimate of the variance, then we can write the direction as sine gradient descent divided by 1 plus the signal to noise ratio. Now this, if you know the Adam literature well, this will ring a bell. But let me just tell you why this is super cool. The thing is, this formulation only holds for beta 1 equal beta 2. It doesn't hold otherwise. And what we are doing really here is drawing a connection between sine gradient descent and Adam through the fact that the second moment estimate here and the first moment estimate are adapted. And that's the only case where you can actually link what is missing between Adam and Signum to a moving average. And you can see down here that if you just remove the secret sauce, what you have is sine gradient descent. So we put them in the same space. It's important to notice one thing. Sine gradient descent with momentum is not a special case of Adam. This might be a little bit of a surprise for some. There is no choice of beta 1 and beta 2 that give you sine gradient descent with momentum. They're not in the same space. Now, but if we put them in the same space, then suddenly we can study them as a continuum. And this is super important for a few reasons. The first reason is that we now have an algorithm. I mean, if you have beta here and choose it to be 0, for example, you call it tau, then you have an algorithm which can be simultaneously Adam and sine gradient descent with momentum. So we can study the interpolation between the two methods. So we draw a link between them, a precise link. Plus, this is also important, this little secret sauce term, you really see also in toy models. Like this secret sauce is exactly the thing that draws the performance, like that drives the performance. And here to do this, we also have a simple toy example. Like take the toy example of this very notable paper, like Zhang et al., like 2024, like last year. What we have is we have gradient descent, Signum, and Adam. And again, we tune the learning rates. We use the same betas for Adam, and we use the same beta, the exact same beta for Signum. And you can see that Signum, you can see this in the picture, the top panel on the right, for an Hessian structure that resembles the transformer, is a little bit worse than Adam. Just a little bit. And you see this exactly in the language model experiments. And so our question is, okay, what's the secret sauce term in this sense? And you can see that here, this is I'm plotting the secret sauce term on a setting where you don't see the difference between Adam and SGD, and you don't see a difference between Signum and Adam, and at a point where you see a difference. And you can clearly see here that the secret sauce term is kind of adapted to the block. So like it cannot be reduced to a single parameter. It really tracks the variance. And you can see this because the variance of the block 3 in the Hessian is much higher. So you see that it kind of tracks the variance, and it kind of works because of adaptation to the variance. Okay, let's go one step further, and let's ask the question, which is a confounder, of course, like what happens if you have a fixed epsilon term? Because when seeing this term, this thing here, you can say, well, that kind of looks like you miss an epsilon here. What about you just place an epsilon? Well, if you place an epsilon, maybe they're the same. Maybe if you tune the epsilon, actually, with secret sauce, the difference between Adam and synchronous with momentum, it would be actually just this little epsilon. But it turns out this is not the case. We have this in toy quadratic models and also in language models. We try for different initialization. We even tune initialization. Epsilon 10 to the minus 3 didn't work. And the best was, like something, like some epsilon, but it didn't matter. It couldn't really improve performance that much. And so really, this term cannot be a fixed term. It has to track something else. It's an adaptive term. So the correction, the secret sauce, is adaptive. So not only sine gradient descent, which is an adaptive method, is the source of adaptivity, but also the secret sauce is an adaptive thing. Okay, but what is it? Right? I mean, it's a variance term, I told you. Can we be more precise? It's a little bit strange also, right? Notice that the sigma square is beta EMA beta of this. Beta times EMA of beta. Why does the beta come in as a multiplier? This was very weird. When I saw it, I was like, too bad. It could have been almost a variance, but of course there is the beta, so it's not a variance. But then Robert came in, and with his knowledge of statistics, which I'm very happy about and very proud to share, and also I learned so much about it, told me, yes, this makes a lot of sense that there is a beta, because this corresponds to a line variational inference. Let me show you what I mean. Let's take at each iteration a new gradient. Let's assume that all gradients come from the same distribution, but the mean and the variance are unknown, and is Gaussian. At each step, we take a new gradient, and we want to update our estimates of the parameter such that this makes sense. And we have this idea that we want to simultaneously update mean and variance of our distribution so that to maximize the likelihood. Of course, also, we don't want to move too fast because that's always a bad idea. So we need a regularization term. So what we have is that at each step, we want to minimize the likelihood of our gradients with respect to our model, plus some regularization, which basically tells our parameter should move slowly. And it turns out that if you solve this minimization problem, you get, for the first term, M, you get exactly the moving average of the gradients. For the second term, you get beta times the moving average. And this little correction, this little beta correction, is specifically because you're estimating parameters at the same time. Like you're not estimating the variance knowing the mean, but knowing an estimate of the mean. And so that's why beta comes in. And it's kind of beautiful that the Adam formula already places that. Now you might ask, is that really, really a big modification? Of course not. But it is interesting that it was already there. Even though kind of no theory was inspiring it, it was kind of there. The proof is actually super simple. I will just say one word about it. Like you can, of course, write down the likelihood for the Gaussian, and you, of course, like the KL divergence between two Gaussian distribution is kind of a well-known formula. What you do is then minimize this term by taking the gradient to 0, and by and what is beta gonna be? Beta depends on regularization, and so that's what you get. And then on the second term, what you really need to do is you need to remember that what you're doing is not estimating given a fixed mean, which is the true mean, but given MK, which is the estimate of the mean, and then you get to this formula, and that's beta times the EMA of the empirical variance. This sounds familiar, right? I mean, some other, like this is also the fact that Adam, there is a first moment over second moment. It's kind of known, right? I mean, first moment over second moment is something that some people just explain it like that, Adam. So it is something that I have no problem. So it's no interaction with the paper. But if you see, there is a paper in 2018 that got super close to this. And you can see that it's basically saying that the sign gradient descent is similar to Adam, but just you have a little bit of a correction term, which is basically exactly what we say, except what we say is that this only holds if beta 1 is equal to beta 2. There's no other setting. And we actually have a proposition. A proposition says, let V be this update rule, which is sign gradient descent plus gamma, because why not? EMA tau, because why not? A times B, like basically I try to be as general as possible, saying, okay, is there any sort of parameters that would lead to the same interpretation? So this thing holds so that Adam can be written like this for some A, B, and gamma, and for some tau, if and only if beta 1 is equal to beta 2. So there's no other choice that would make sense for this sort of interpretation. The interpretation that the correction factor, therefore the secret sauce, is a variance only holds in this sense. Is this a limitation? An excellent question. I think not, because when we assume that beta 1 is equal to beta 2, we don't lose much performance. Of course, it's not as good as training 3 hyperparameters. Of course, 3 hyperparameters is always better than 2. But beta 1 equal to beta 2 closes a lot of the gap. And therefore, we are kind of more excited about the fact that this is like, aligned with the level and it's telling something a bit more than sign gradient descent that we can understand a little bit better. And also, like, just shout out to, we will have another talk about Adam. Now I'm done, by the way. Theodora is, Theodora is having did an internship with me and with Jonas Skyping, like here at the Max Planck Institute. She's going to talk about the effect of batch size in Adam, which is super interesting. And with that, I just thank you very much. And if there are some questions, I'm very open to that. Yes, thank you.
Thank you so much for an amazing talk. If anyone has any question, feel free to unmute. There are a few questions in chat as well.
Yes. Should I just read the questions or just check? I think I can check. Does statistical convergence guarantee? Oh, okay. So there's a few questions. Okay. So there's like one thing about the DNA modeling scale. I mean, DNA. Sometimes people in DNA have 1 million context, or it's been it's been reported that it's actually important to have. Some people have different opinions. For example, me. But the important thing is that you cannot really scale attention to this context without doing further tricks. You have to do tricks, otherwise it's impossible. So it's important to go beyond that, and therefore it means it's a good thing to think about models that go beyond, but those models can be difficult to optimize. Is the learning rate constant for the table where more data is? But no, it's not constant. We have 7 learning rates, and we pick the best. Excellent question. Yes. So this is for more data. Also, we do all the hyperparameter tuning. It's not constant. Then we have why does theoretical convergence guarantee matter so much in the literature? Speed in practice matters should matter more. I mean, the thing is, at least in some simplified setting, one would love some sort of guarantee. I agree that theoretical convergence guarantee might be a bit of an overkill, especially if the setting is... So there is no theorem, and there will never exist a theorem saying if you have a non-convex loss function, then if you use Adam, you will be faster. I mean, there are some... under some assumptions, one can say something a little bit, but it definitely doesn't motivate the... So yeah, I agree. We should be a little bit more coherent. I mean, one setting, for example, where people have been used, I mean, there's, if you know L0, L1's smoothness, this is important, like to have an adaptive method, because you can say that SGD, if you don't normalize or if you don't have clipping, then it's actually not converging. It can diverge. for this setting. X to the fourth power is an example, or some strange noise structure. I can so slides. I don't know if there is a place here to share them, but I could share. If you send me an email, I'll just send them. Do you think there is a connection between optimizer dynamics and loss of plasticity? Yes, of course there is, because a loss of plasticity probably depends. I mean, the all continual learning thing depend on the structure of the hash and the kind of adaptation that you have, and the different optimizers have different inductive bias or implicit bias with respect to what Bayesian do they choose. So makes sense, right? But like that they have there is a relation between that and loss of plasticity. For example, just saying SGD on simple problems might select a wider minimizer. That implies that basically if you change the parameters a lot, you would have less you can be a little bit more plastic at the beginning. So if you adapt to a second task, and if you were flat, then it means that you will be good also on the previous task when you start to optimize again. That might be a relation, for example. Interesting questions. If there is any other question, yeah, okay, you can also just ask me by email. Why you put beta equal 1 over 1 plus lambda? No, this is just like, this is just the beta that comes from the theory. It's not a choice that we make. It's basically saying, okay, if you have the regularizer that looks like 1 over lambda times the KL divergence, then it comes out that beta is equal to that. It doesn't matter what it is, because there is a beta that point. And then the optimal beta depends on the level of regularization that you want, which is an hyperparameter. So you can either tune lambda or you can tune beta. It's anyways a hyperparameter. So it's not a choice. It's just what happens.
I think there's one more question. Can we predict if we are at a bad optimizer hyperparameter in the first few epochs instead of training till convergence? It's the second last question, Chef.
Sorry, can you repeat a little bit? I think I lost a little bit the beginning of the question.
So it's the second last question in the chat.
So if you have okay, the last question you said is about beta equal to 1 over 1 plus lambda. So this is not a choice. Like if so your question is about what happens if? Sorry.
So it's the second last question. I think you.
Sorry. Okay. Can we predict whatever? Sorry, I missed the question. Can we predict if we are at a bad optimizer per parameter? Yeah, that's a good question. Very good question. Unfortunately, no. If you do things the standard way, there are tricks. For example, there are these, I don't remember how they're called, but there are this kind of speed runs thing. And I'm not talking about NanoGPT speed runs. I'm talking about at some point, people were doing this crazy things where they kind of like exponentially increasing learning rates. I remember something like that. There are some ways to tune the learning rate that are like just, you test your sensitivity of your model by changing your learning rate. Like you just start to optimize and then you change your learning rate up and down, and you just try to see when is the instability coming in. You could use that. I've never seen it in language models. Usually, if you just judge from the very first iterations, you will be very fooled, because it could be that SGD is actually much better at the first very few iterations. Bit of a tangent. How many experiments did you total together? Seems to be the thousands, that around 2,500, I believe. I mean, I would claim in the latest, I would claim 2,000. There are definitely runs that I didn't report, and a lot of them. So let's say 2,500. But yeah. Should the PyTorch set hyperparameters with the same values instead of? I mean, you should definitely don't use the default of Adam. The default for language modeling is 09095. You can find this, for example, in the PTA configurations. If you believe me, 9595. But only if you believe me, but you don't have to believe just me. There's excellent papers by For example, Sean Kikada in the group saying that actually beta 1 should be 95, and then beta 2 was already 95. So again, we're not the only ones saying this. We're definitely not the only ones saying that beta 2 is too big. Of course, there is also a paper saying that is called, I think, your choice of beta 2 might be too large. So yeah, no, definitely not 999. Definitely not. That's a disaster. I think the original paper uses that, but I don't know why. Perhaps the batch size was too small. And then the first beta 19009 is not too bad, but I found one experiment, one setting like if you have like half a billion parameters, I actually found that 09095 was pretty suboptimal for all learning rates. Like, I mean, for the best learning rate, you couldn't save you. You really needed to tune the beta 1 to be bigger. So yeah, strange things, right?
Great. So I think we are 2 minutes above the time. We can conclude it here. Thank you so much, Antonio.
Thank you.
For
Thank
wonderful.
you.
So
Thank you so much.